Hi, and welcome to this video. Today we're going to cover free body diagrams, net forces, and Newton's second law. So to start, let's talk about free body diagrams. Firstly, what is a free body diagram? Think of the word free, and I think of all sorts of different things. Here are some examples of free used in other senses. However, none of these really are what we're going to be using the word free for in physics. So let's get a definition of free body diagrams in physics class. Free body diagrams are a way to determine and illustrate all applied forces on an object or body. So let's get an example. Here we have this man in blue pushing a wooden block on a frictionless surface. Let's lay out a process for making a free body diagram. The first step of the process is to determine what the object or body is that we care about. In this instance, we care about the wooden block. We care about the wooden block because that is the object that the forces are being applied to. The man is physically applying a force to the block, so that's what we care about. We then need to draw a box on its own to represent our object. So here's a box on its own. This is the beginning of our free body diagram. Note that regardless of what our object or body was, we're always going to represent it with a square. This could be a car, it could be a block, it could be really anything, but it's always represented by a box. Next, we need to determine all the forces being applied to this body. So in this case, we have one man on the left exerting a force on the block to the right. So we're going to add that arrow in onto the right. Note that the force vector arrow goes off of our box that we drew, and we write an F right above it to represent that there is a force acting right there. So let's go on and do a couple of examples of making free body diagrams. Here's an office chair race. So during lunchtime, employees at a paper company decide to race on rolly chairs. Phil here pushes Carla with a force of 20 newtons during the race. Draw a free body diagram to represent this scenario. Let's start. As always, we draw our square to represent our body here. Our body in this case is the chair with Carla in it, all as one body. We then draw in our force vector. Here we have a force, F subscript P, P for Phil in this case. This represents the force that Phil is applying onto the chair. In this case, it's 20 newtons, so we have it that it's equal to 20 newtons. Note that the arrow points left this time because Phil is physically pushing to the left. All right, so this is a relatively simple free body diagram. Let's do another one. So here we have a friendly tug of war. Over the weekend, Charlie and Sam want to hang a tire swing, but they both think they can hang it themselves. They begin to argue, then both tug on the rope needed to hang the swing. Charlie pulls with a force of 7 newtons. Sam pulls with a force of 4 newtons. Draw a free body diagram to represent the forces acting on the rope. So in this case, again, we start with our box, but in this case, the box actually represents the rope in this problem. Then we have to start adding in our forces. So what's the first force we think of? Well, we see that Charlie pulls with a force of 7 newtons. So we'll add that in. Note that Charlie is pulling the rope to the left with a magnitude of 7 newtons. So we have F with a subscript C for Charlie and the magnitude of 7 newtons on our free body diagram. We're also going to add in the force that Sam applies to this rope with an F subscript S for Sam and then a magnitude of 4 newtons. So here we have our free body diagram, which displays our object along with all the forces being applied. Here's a third problem, box of toys. 2 boys are helping their mother move a rather large box of toys. Tommy pulls the box with a force of 2 newtons, while Ross pushes with a force of 3 newtons. Draw a free body diagram representing the applied forces on the box and determine the net force applied. Okay, so once again, we start our free body diagram by drawing our square here. The square represents the box of toys in this case. So we first look to see what forces are being applied. We notice that Tommy pulls the box with a force of 2 newtons. In the picture, we see that Tommy is pulling to the left. So we draw our force vector going to the left. F subscript T for Tommy with a magnitude of 2 newtons. There's also a second force in play here due to Ross. Ross pushes with a force of 3 newtons. So Ross's force actually also goes to the left because he's pushing the box from behind. F subscript R for Ross is equal to the magnitude of 3 newtons. This is our entire free body diagram here because we just have the box of toys with 2 boys applying their forces. The question also asks us about net force. So net force is something that you guys have heard before, so I'm not going to describe it too much, but it's basically just the overall force acting on the box. So in this case, we have 2 forces acting that we have to sum here. We have the force due to Tommy. We also have the force that Ross is applying. So we have Ft for Tommy plus Fr for Ross. Now we're going to plug in our numbers. Notice here that Tommy's force is negative 2 newtons. His force is, of course, negative because due to sign convention, things that move left are always negative. So we have negative 2. Then we add in Ross's force, which is negative 3. Again, that's also negative because it's also directed in the left direction. So that leaves a total net force of negative 5 newtons. So there are negative 5 newtons of force being applied onto this body to the left. Okay, so now we have another problem. So Manu Ginobili and Mike Henry fought for the ball in an NBA game back in 2018. Ginobili pulled on the ball with a force of 25 newtons, while Henry pulled on the ball with a force of 18 newtons. Draw a free body diagram representing the forces applied to the basketball. If the ball is half a kilogram, solve for the net force and the acceleration of the ball. Okay, so once again, we're starting with a free body diagram here. So we start with our box. We're first going to add in the force that Manu Ginobili applies to the box, or to the ball in this case. So we have F subscript G for Ginobili is equal to a magnitude of 25 newtons, because that's how much force he puts on the ball. We also have a force due to Mike Henry, H for Henry on the right. He's pulling the ball in the opposite direction, so it goes right, with a magnitude of 22 newtons. We see here that the mass of the object is 0.5 kilograms. We'll use that in just a minute. We're also looking for the net force here. So that was the entire free body diagram. We had our object as well as the two forces being applied. We also want to find the net force. So to find the net force, once again, we're going to sum or add together all of our forces. Here we have the force due to Ginobili plus the force due to Henry. So we plug in our values. We have negative 25 for the force of Ginobili, and we have positive 22 newtons of force due to the force of Henry. That leaves us with a total net force of negative 3 newtons. The question also asks us to solve for the acceleration of the ball. So we're looking for the acceleration of the ball due to the net force on the system. So let's plug in our equation for the Newton's second law. You'll recall the Newton's second law is F equals ma. Here we're going to use F equals ma, but we're also going to connect in F net. So we're using a net force here, where we have the net force on the system is equal to the mass. Here the mass is the mass of the basketball times the acceleration. But in this case, we're not solving for F net. We need to get acceleration on its own before we plug in numbers. So we're going to divide both sides by an m. We can do that so that the m's on the right will cancel. We now have the net force divided by mass is equal to acceleration. We're solving for acceleration, and it's now on its own, so we can plug in some values. The net force we just solved for is negative 3 newtons, and the mass of the ball is half a kilogram, so we have negative 3 divided by 0.5. That leaves us with an acceleration of negative 6 meters per second squared. That is our final answer. So in this problem, we drew a free body diagram, which represented all the forces acting on the ball. We then figured out what the net force on the ball was between the two forces, and then we were able to solve for the acceleration of the ball using Newton's second law, which is force equals mass times acceleration. All right, here's one last problem. Some fun with corgis. So 3 corgis are playing with a 0.6 kilogram rope toy. Carl the corgi, on the left, pulls hard with a force of 8 newtons. Chloe and Cooper, the corgis, each pull the toy to the right with a force of 3 newtons. Draw a free body diagram representing the forces, and then solve for the net force and the acceleration of this toy. So once again, we're starting with our box for our free body diagram. The first force that we're going to take into consideration here is the force due to Carl. Carl applies a force of 8 newtons, and he's pulling to the left. So our force goes to the left of the box. We also have forces due to Chloe of 3 newtons to the right, and a force due to Cooper of 3 newtons, also to the right. So this is our entire free body diagram because we have the 3 corgis all pulling on this toy. Carl pulls to the left, and Chloe and Cooper both pull to the right. So now we need to figure out our net force. Again, the mass was given, so we're going to use that in just a second. But to calculate the net force here, we're going to find the sum of all the forces, or we're going to add all the forces together. Here we have the force due to Carl, and we have the force due to Chloe, and we have the force due to Cooper. So we're adding all of them together. Now plug in values. So we have negative 8 for Carl's force because he pulls the rope to the left. We have Chloe is a positive 3, and Cooper is also a positive 3. So when we add those together, we get a net force on the toy of negative 2 newtons. So there's a magnitude of 2 newtons being applied to the toy in the left direction. All right, so now we need to solve for acceleration once again. So to solve for acceleration, we're going to use Newton's second law, which is force equals mass times acceleration. But once again, in order to find the acceleration of the toy, we're going to use the net force that's applied to the toy between the 3 dogs here. So once again, we're solving for acceleration, so we need to get a on its own. We're going to divide both sides by m. The m's on the right will cancel, so we'll have the net force divided by mass is equal to acceleration. We can now plug in our net force of negative 2 and our mass of 0.6 kilograms. When we solve that out in a calculator, we get that the acceleration of this rope toy is negative 3.3 meters per second squared. So in this problem, again, we were able to draw a free body diagram representing all the forces acting on this toy. We were able to figure out what the net force on this rope toy was, which was negative 2. We were also able to determine what the acceleration of this rope toy was. So in this video, we covered free body diagrams, net forces, and Newton's second law. Thanks for watching.